Hey everyone, so this is the solution video for Worksheet 4.1. We're going to be talking about rational functions in this one, and we're going to start off in number 1 with a rational function f of x is equal to x divided by 3x minus 6. So it's a pretty simple rational function, but it still follows the definition in that in our numerator here, we've got a polynomial, and in our denominator, we also have a polynomial. So both of these functions in the top and the bottom will be polynomials. In the context of this video, I may refer to our top polynomial as our numerator, or I may just call it our top polynomial. And for the bottom, I may refer to it as the denominator, or sometimes just our bottom. So just as a point of reference for what I'll be referring to here. So in part A, we're asked to find the domain of this entire function. And since we're dealing with polynomials, it's nice because polynomials we're usually allowed to plug in whatever we want to. And the domain is all real numbers. In the case of a rational function, however, we need to be careful because we don't want this bottom polynomial to work out to be a 0. Otherwise, we'd be dividing by 0. So the way that we identify the domain of a rational function is we say, well, let's take the denominator of my rational function, in this case f of x, and I want to make sure that I pick x's such that this is not going to be equal to 0. So we can just sort of solve this non-equality here. So here I'll go ahead and I'll add 6 to both sides. So 3x can't be equal to 6. I'll divide both sides by 3, and we'll notice that x cannot be equal to positive 2. So this is our restriction. Specifically, it's the restriction on our domain. So if we wanted to go ahead and now define what our domain is, so for the domain, what I'm going to go ahead and do is I'm going to set up a real number line. And this is going to go from positive infinity to negative infinity. And our only real issue here is going to be at positive 2. Specifically that we can't include it, so I'm going to put an open circle over positive 2, and notice that I can take anything that I want all the way from positive 2 to negative infinity, and I can include anything from positive 2 to positive infinity. So if I was to identify the domain here in interval notation, we'd be going from minus infinity to positive 2, not including it, and then union that with the interval from positive 2 to positive infinity. So that would be interval notation for a pretty basic idea, which is that x can't be equal to positive 2 for this function. Again, otherwise we'd have a 0 in the denominator. So for part B, we're going to go ahead and we're going to identify the vertical asymptotes. Now, the first thing that we're going to want to ask ourselves before we go and find the vertical asymptote is f of x simplified? Because in order to really identify this, we want to make sure that we can't cancel, if we can cancel out any common factors in the top and the bottom, that we've done so. In this case, there's really nothing that we can do to simplify this function, so yes, we're dealing with a simplified version of f of x. And in general, the reason that we want to do this is that all vertical asymptotes, which I'm just going to abbreviate as VA, vertical asymptotes are always going to be equal to the zeros, 0 or zeros, of the simplified denominator. And again, simplified is key here. We'll see this in another example why we need to make sure we've simplified the denominator. So you've probably discussed this in class, but it's a good thing to talk about. So let's go ahead and take our simplified denominator, which in this case is just 3x minus 6. And we want to find the zeros of this. So we're going to set equal to 0 and solve for x. This looks pretty familiar. We've kind of done this already. So if we go ahead and we solve this, we're going to get x is equal to positive 2. So this is going to be our vertical asymptote. And this should make sense in the context of our domain in that our function's not defined at this asymptote. And that's why we couldn't include 2 in the domain of our function. So hopefully the domain now seems to make a little more sense in the context of identifying this vertical asymptote. And again, vertical asymptote is going to kind of look like an invisible force field that runs vertically through the point x equals 2 on our x-axis. But again, we'll see a little bit more of the graphic interpretation of that later. Okay, so for part C, we're asked to identify any holes in the graph. And in order to do this, we kind of want to ask ourselves this question. So do the top and the bottom, again, our numerator and denominator. So do the top and the bottom of f of x, our original function f of x, have any common zeros? And we could think about it in terms of common zeros, or in other terms, we talked about this connection between zeros or factors, so the idea of identifying a common factor may also be another way to consider it, or common factor. So that's what we're going to want to ask ourselves. So let's think about this. Well, in the top of our function is just x. So x equals 0 will be the only 0 of our numerator. And for the bottom part of our function, we've determined that x equals 2 is the only 0. So again, referencing back, this function f of x is x over 3x plus 2. The 0 of the top is 0. The 0 of our bottom is going to be 2. Clearly, these are not the same. We don't have any common zeros. So from this, we can conclude no, there are no common zeros. And because of this, this implies that there are going to be no holes. So there are no holes in our function f of x. So we're going to make this distinction between the idea of common factors or common zeros and holes. Okay, so part D, we're asked to determine if, or find the horizontal asymptote if it exists for this function. Now what we're going to want to do with horizontal asymptotes is we're going to pay close attention to the degrees of our top and bottom polynomial. So in this case, we're going to want to note the degrees of our top and bottom polynomial, because that's going to sort of tell us what type of horizontal asymptote we're dealing with, if in fact there is one. So again, let's look at the top. Now if we look at the top, it was just x. So the polynomial x has a degree of 1, because it's the highest power. And for the bottom, in our denominator, we're dealing with 3x minus 6. And again, the degree here would be 1, because it's a linear function in both cases. So what we see in this case is that the relationship between the degrees of the top and the bottom, in this case, they're equal. So there's 3 rules that you've probably discussed in class in terms of the possibilities. In this case, we've got the possibility where the degrees are equal. So since the degrees are equal, then there exists a horizontal asymptote, which I will abbreviate as just HA, at the horizontal line y is equal to a divided by b, where a and b are the lead coefficients of the top and bottom. So again, we've got polynomials in the top and bottom. In Chapter 3, we talked about identifying the lead coefficients, and this is respectively. So let's go ahead and identify these lead coefficients then. So if we've got the top is just x, so our lead coefficient is going to be, if we're dealing with a over b, our lead coefficient is going to be 1, and the denominator, our lead coefficient for 3x is going to be 3. So this implies that we have a horizontal asymptote at y is equal to 1/3. So we're going to have a horizontal line, well, an invisible horizontal line sort of running through this, and we'll see in a second what this implies in terms of the graph. Okay, so for part E, it says use a graphing utility to basically graph the function, and then we can describe the behavior of our curve as we get closer and closer to these two asymptotes that we've just identified. So I'm going to go ahead and bring in a graph. So if you were to graph this on your calculator, you should get something that would look like, bing, this. Probably not all the pretty colors, but and even the horizontal and vertical lines wouldn't work in. But you get something that would somewhat resemble this. So what we would like to do is figure out some way for us to describe what's going on at these asymptotes. So let's go ahead and first make sure that we're clear on our asymptotes. This red line here, this is our vertical asymptote, and it's the line x equals 2. And then we've also got our horizontal asymptote, which is this blue line. And this is our horizontal asymptote. Specifically, we determined this is the line y equals 1/3. And we can see that's passing through y equals 1/3 here, and our vertical asymptote is passing through x equals positive 2 right there. So let's try and describe the behavior around our vertical asymptote first. So for the vertical asymptote, x equals 2, let's see what our curve is doing. So again, our curve is the black line here. So we want to see, well, what is this doing the closer and closer we get to our vertical asymptote? Well, it kind of looks like we got a force field here. So one way we could think about it is that as x approaches 2, let's say from the left. So let's say our x values are coming in from the left along the x-axis here. So coming from negative infinity, our x values are getting closer and closer and closer to positive 2. So to signify that we're coming from the left, I'm going to put a negative sign, sort of as that superscript. So as our x values get closer and closer to 2 from the left, our curve, which is the black line, just seems to get dropping. In a dropping fashion, it keeps going lower and lower and lower. It almost looks like it's going to end up dropping all the way down to negative infinity, which is what we would say. So as our x values get closer and closer to 2 from the left, our function, f of x, is going to get closer and closer and closer to negative infinity. Similarly, if we were to consider, well, what happens if we approach this vertical asymptote from the right? So let's say we decide to come from the right. So our x values are coming from positive infinity, and they're just kind of coming in on 2. Well, as we get closer and closer to positive 2 from the right, our curve, the black line, seems to be getting bigger and bigger and bigger. It's running into this force field, but it's getting shoved up towards positive infinity. So that's how we're going to describe that behavior at this asymptote, that f of x is approaching positive infinity. So depending on which side we're coming from, our function is either going to go to positive infinity or negative infinity. And we see this with all vertical asymptotes, that it's going to go one way or the other. This is also a topic we have in calculus where we talk about limits. So that's how we could think about talking about the behavior of our vertical asymptote. Now let's consider our horizontal asymptote. So for the horizontal asymptote, which in this case is the line y equals 1/3, this is essentially end behavior. We talked about the end behavior of polynomial functions. Now we're going to be looking at the end behavior of rational functions. So as with the end behavior of polynomials, we want to know, well, as x gets bigger and bigger and bigger, let's say in a positive direction. So as x approaches positive infinity, so our x values, instead of getting to 2, now our x values are headed out the real number line all the way to positive infinity. Well, what is our curve doing as our x values get larger and larger and larger? Well, it seems to kind of just slide down up against our blue line, our horizontal asymptote. It kind of just like snuggles up next to that horizontal asymptote. So we could imagine that the further we go out, the closer and closer that black line is going to get to our blue line. And we know that the value of that line is y equals 1/3. So as x gets infinitely large positive, our function f of x is going to approach a value of 1/3. Similarly, if we were to take our x values out to the negative side of the real axis, we see that our line gets our function, gets closer and closer to that blue line, y equals 1/3, our horizontal asymptote. So we could say that as x approaches negative infinity, our function f of x is also going to approach that value of 1/3. And again, this is the end behavior. So as our x values reach the end of the real number line, our or the ends of the positive and negative side, our function is going to approach this horizontal asymptote that we found. That's a connection you want to keep in mind here with rational functions, that end behavior is linked with the horizontal asymptote in that value. Okay, so that takes care of this first one. So the second one, exact same process that we're going to go through. Just a slightly different function, a little bit more going on that we want to be careful of. So let's go ahead and check this one out. So our function now is x squared minus x minus 12 over x squared plus x minus 6. Well, what I would really encourage you all to do as a first measure with these is, let's go ahead and, if possible, let's factor this first. So if when possible, let's go ahead and factor first, and we can kind of take it as we go from there. So let's see what we can do here. So if we factor this, the top we can factor as x minus 4 times x plus 3, and then we can divide this. X squared plus x minus 6 is going to factor as x minus 2 times x plus 3. Okay, so once having this factored is going to make these next steps a whole heck of a lot easier. You can't always do it, but a lot of the ones you're going to run to are going to be set up so that they do factor nicely. So with this one in mind, let's go ahead and find the domain of f. So again, just like we said last time, the domain of any rational function is all real numbers except for the numbers that make the denominator equal to 0. So we can figure this out by taking our denominator, which is x squared plus x minus 6, and saying I do not want this to be equal to 0. We want to find the x values that fit this. We've already got it factored, so we could rewrite this as x minus 2 times x plus 3 cannot be 0, which tells us that we have two choices here. We don't want x minus 2 to be equal to 0, and we don't want x plus 3 to be equal to 0. So when we take these two together, we realize that x cannot be equal to positive 2, and it cannot be equal to negative 3. So again, these are our restrictions on our domain. And these are the only restrictions. So when it does come time to find the domain of this function, we're going to want to get ready to put this in interval notation, and if you have any trouble with that, a real number line is a great place to start. So the only values we want to be careful of are negative 3 and positive 2. So we can go ahead and we can write our domain as, well, we don't want to include negative 3, we don't want to include positive 2, but we sure as heck want to include everything else in between. So all of these numbers on the real number line, from negative infinity to positive infinity, except for negative 3 and positive 2, are going to be included. So our domain will be equal to the interval from negative infinity to negative 3, not including negative 3, and then from negative 3 to positive 2, excluding both of those points, and then from positive 2 to infinity. So this would be our domain in interval notation. You always want to be careful and make sure that you're putting it in the correct notation given the problem or the homework. Okay, so next we want to identify any vertical asymptotes from this graph. Now, as we talked about last time, the first thing we want to check for identifying for vertical asymptotes is f of x simplified? So we want to make sure that it's simplified. Well, let's go check. And this is why factoring is a good first step. So if we look up at our function, we see that there is actually a common factor that we could cancel out, which is the x plus 3. So in its original form, no, it's not simplified. So we want to go ahead and do it. And if we simplify, we're going to end up with f of x is equal to x minus 4 divided by x minus 2. So this is the simplified version of f of x. This is what we want to work with when we're identifying our vertical asymptotes. Because again, as we talked about last time, the vertical asymptotes are essentially just the zeros of the simplified denominator. Now that we have a simplified denominator, we can go ahead and solve for it. So we're going to take x minus 2, set it equal to 0, and that's going to give us a vertical asymptote at the line x is equal to 2. So there is our vertical asymptote. So the question is, well, what happened to that x plus 3? Where does this factor in? Well, this is actually what we're going to worry about here in step C. So we want to identify any holes in the graph. And just like we did last time, in terms of answering the question of are there holes in the graph, we want to first consider, well, are there any common zeros? So if we go back to our original function f of x, and again, this is the same thing as asking, well, are there any common factors between... Oh, sorry, we got a little fire going on somewhere. So are there any common factors? Well, if we go back to our original function, in factored form, there is a common factor that we canceled out, the x plus 3. So we're going to go ahead and we're going to say yes, there are common zeros, and the common factor is in this case x plus 3. Or the actual common zero is going to be x equals minus 3. So we notice that it's a common zero. If we were to plug in our original function f of x, if we were to plug in negative 3, we would end up getting 0 divided by 0, which is sort of a warning for us. So we can sum it up this way. There exists a hole in f of x when, and what we could do is we could take that common factor x plus 3, we could set it equal to 0, and we'd see that there exists a hole when x is equal to negative 3. Well, we want to actually find the exact location, because this is like a really small empty point in our graph. So not only do we want to know the x-coordinate, but we're probably going to want to find the y-coordinate. So next, we find the y-coordinate of the hole. And we're going to do this by plugging it in. So plug x equals minus 3 into the simplified function. So into the simplified function. We already talked about if we plugged x equals negative 3 into the original function, we just end up getting 0 over 0. So that's why we have to use the simplified version. So if we do that, and we find f of minus 3, and we plug it into the simplified version from part B, we get minus 3 minus 4 divided by minus 3 minus 2, which would give us a value of negative 7 divided by negative 5, or just 7/5. So finally we can conclude that there is a hole at the point x equals negative 3, y equals 7/5. And you're not going to really see this on your calculator unless you zoom in super close to this specific point. You'll see a little missing pixel. But for the most part, your curve is going to behave as if nothing's wrong, and it's going to look just like the curve would at that point. Okay, so part D, we want to find the horizontal asymptote if it exists. And we'll consider what we did last time is we'll look at the degrees. So look at the degrees of the top and the bottom and see how they relate to each other. In this case, that we're going to note that the degrees are equal. And lots of times you may wonder, well, do you use the original function or do you use a simplified function? Well, it's not really going to make a difference. We can notice that in the unsimplified form, the degrees are both 2, and in the simplified form, the degrees are both 1. So even if you cancel out a common factor, the relationship of the degrees with each other will stay the same. So the degrees are equal, and that means that we're going to have a horizontal asymptote at the line y is equal to the lead coefficient of the top divided by the lead coefficient of the bottom, which in this case is just 1 divided by 1, or 1. So we've got a horizontal asymptote at the line y is equal to 1. Okay. So the last part asks us to graph the function using a graphing utility and describe the behavior of our curve near the asymptotes. Well, let's go ahead and bring in a curve again. And we have our vertical asymptote, namely x is equal to 2. And then we've also got our horizontal asymptote, namely y is equal to 1. So very similar to what we did last time, we can say that for the vertical asymptote, our behavior of our curve, which again here's the black line, this is what we're interested in. So as we get closer and closer to x equals 2 from either side, our curve is going to, on the left, go up to positive infinity, and on the right, drop down to negative infinity. So again, as we're approaching the x values from the left of 2, our curve is going to shoot up to positive infinity. And as we approach to from the right, our curve is going to shoot down to negative infinity. And that's how we could in turn describe that. So I'll get those lines out of the way. So as x approaches 2 from the left, that's what that negative is for, our function f of x is going to approach positive infinity. And as x approaches 2 from the right, our function f of x is going to go down to negative infinity. It's going to drop down the y values. And then for the horizontal asymptote, which again is essentially the end behavior, and with end behavior we know that we're looking at x going to positive infinity and x going to negative infinity. We see that on both sides of this line, our curve f is getting closer and closer and closer to that horizontal asymptote of y equals 1. So we could say that as x goes to positive infinity, our function is going to get closer and closer to a value of 1. And as x approaches negative infinity, our function is going to approach a value that gets closer and closer and closer to positive 1, again, from the horizontal asymptote. Okay, so that does it for the solutions for Worksheet 4.1, and I will see you all next time.